welcome into week 2, right? So moving into a new chapter, we start to talk about sequences. Right now, there'll be a definition that pops up there. I'll leave it there for a second, but essentially you could think of a sequence, we'll say, as an ordered list. Let's say that first. And the way we're creating or getting these things in this ordered list is from a function, right? This is essentially what the sequence is. It's a function mapping the natural numbers to the real numbers. Now, the real numbers are any decimal, right? Or any number you could possibly think of other than complex values. And the natural numbers are the counting numbers, 1, 2, 3, 4, etc. Right, so that's what's meant by this fancy math notation over here. Right, and so it's kind of a little bit hard to think about how can it be an ordered list and also a function. So let's just jump right into an example and we'll go through it. Right, so the very first thing that we're going to need to know is, well, what are we looking for? So we'll go ahead and list the first 5 terms in our sequence. And we'll talk about some notation here too. Right, so the sequence that I'm going to give you is going to be in the form of a sub n. So a sub n is known as the general term, right? It can be any of the terms in the sequence, but we're going to say this is equal to -1 raised to the n. We'll do n minus 6 all divided by n factorial. Right, so this is known as the general term. Let's use a different color. General term. And essentially, so if you gave me some value, right, some position in your ordered list, I could give you the term in that position. So let's walk through it. So let's say the very first number here, as a reminder, we'll put it over here, right? The natural numbers starts at 1 and it keeps going, right? Just our counting numbers. And so for our first thing, we'll say, well, what is going to be in our first position of our ordered list? Well, that means I need to plug in 1 and I would get my term a sub 1. Right, so it makes sense anytime I see an n now, I'm just going to go replace it with a 1. And I'll do all the calculations here first as we move. There's 5 of them. I'll start shortcutting a little bit of the algebra here. -1 to the first, -1, 1 minus 6, -5, all over 1 factorial, which is 1, so we just end up with +5. And we'll write our list down here. So let's go ahead. We'll just say our ordered list, our very first position here is a 5. Okay, we'll move on to our next one, right? Going in order. So what's in our second position? Well, that's when n is equal to 2. Right, it gives us our second term in our sequence, and again, we're just plugging in 2 for n. 2 minus 5, all over 2 factorial. Okay, -1 squared, +1, right, I don't need to write +1. 2 minus 5, -3, all over 2 factorial, which is 2 times 1, or just 2. And so we have our answer, right? -3 over 2. So guess what? In our second position, we have -3 over 2. And we're just going to keep repeating this process for the first 5 terms, which would be 1, 2, 3, 4, 5, right? Let's go and we'll do our next one, and then maybe pause the video after we work together on 3 here, which is a sub 3. Now I'm going to shortcut another step, so I'm going to keep trying to subtract steps. -1 to the 3rd power. negative 1. Right? 3 minus 6, negative 3. I'll leave this. 3 factorial is going to be 3 times 2 times 1, right? So we end up getting 3 over 6, which is equal to 1/2. So over here, our third term, 1/2. Right, so pause the video, go ahead and try to do A4 and A5 on your own. Right, all we're doing is plugging in 4 and 5 into our general term sequence. Right, this is the function. Right, so when we're talking about the function, I'm taking a natural number, 1, 2, ... plugging it into my function, and it's going to spit out a real number in this case. Okay, so hopefully you pause the video. I'll go ahead and do A4. So over here, we'll do A4. Right, well, what is that? That's when n is equal to 4. We plug it in. Negative 1 to the 4th power, positive 1. Right, anytime it's going to be odd, this part is going to be a negative number. Anytime it's even, it's going to be a positive. 4 minus 6, negative 2, over 4 factorial. And if we already know 3 factorial, which we know to be 6, real quick, just as some side work, let's put this here. If I have 4 factorial, I know this is 4 times 3 factorial. Right, so if I already have 3 factorial, which is 6, I just need to multiply by 4. Right, and I get my answer. And this simplifies to negative 1 over 12. I'm going to run out of space for that 5th one, but you can fill that out after you get it. Now, something to know before we do this last one here is notice positive, negative, positive, negative. What is making this happen is this piece here. Right, this negative 1 to the n is known as the alternating piece. It's flipping us back and forth, right? Going from, in this case, positive to negative, depending on what's happening here as well. But we're going back and forth as we're finding our terms. Okay, let's use this one. We'll do A5. So again, anytime it's a negative, negative 1 to the 5th power, we'll have a negative value. 5 minus 6, negative 1, all over 5 factorial. So again, I already have 4 factorial, so all I need to do, one more time in case we missed this, 5 factorial is equal to 5 times 4 factorial. So I have 4 factorial, 24. I just need to multiply that by 5. I get 120. 1. Right, so that's all it's asking for when it's looking for the first 5 terms. There is a different kind of style where it's going with a recursion. So for the computer science people, you're familiar with recursion already. But we will do that example in the next one here. Again, just the definition hopefully popped up. Sequence an ordered list. Right, so this keeps going, right? This is an infinite list. For our case, we would cut it off at 5. I couldn't fit that, but you could imagine comma 1 over 120 would fit here. Right, and then this a sub n is known as the general term, right? It's general in the sense of whatever you give me. So if you gave me the 64th position, or you wanted to know what's in the 64th position, I could plug it in and I could tell you what that number would be. Okay, all for this example. I'll see you in the next one. Back to example 2. So same as the previous example, there's just one little twist. Right, so the twist here is going to be recursion, right? So the way that we're going to define this sequence now is going to be through recursion, right? Recursion just means we're going to call the function within the function. And you'll see what I mean when we get to this example. All right, so we'll call the function within the function. So we'll do the same thing. The question should pop up somewhere. we're going to list out the first 5 terms, and I'm going to tell you the first term. So I have to tell you the first term if I'm going to define this recursively. So let's say a sub 1 here is equal to, let's do 4, right? And I'm going to define my function saying a sub n plus 1. So the very next term is going to be equal 3 times the previous term, and this is what I mean, I'm calling the function within the function, divided by, we'll just do a sub n minus 5. That's fine. All right, so I'm calling the function within the function, but everything else remains the same, right? So now it's going to ask you for the first 5 terms, and you go, okay, well, guess what? The first one's already done for us. A sub 1 is equal to 4. Boom, 1 is done. Now we go into a sub 2. And what do I notice here? I'm going to break this down as much as I can. A sub 2, which I know to be, right, a sub 1 plus 1 down here. This is a mini plus sign, right? I'm trying to make it look just like this, n plus 1. So now 1 plus 1 must be equal to a sub 1, right, 3a sub 1, sorry, all over a sub 1 minus 5. And I already have what a sub 1 is, so I'm calling back to the previous iteration and saying, well, 3 times a sub 1 is 3 times 4, all over 4 minus 5. So we have 12 divided by negative 1, or negative 12. Okay, and we just keep repeating this process. So now we have a sub 2 figured out. So when I move on to a sub 3, right, a sub 3 here is going to be equal to, well, this is the same, right, just rewritten. So now I'm looking at 3 times a sub 2 all over a sub 2 minus 5. And now I'm looking at the previous iteration. And I'm going 3 times a sub 2. Well, a sub 2 is negative 12. A sub 2 is negative 12 minus 5. We end up with the ugly negative 36, but it's also going to be negative on the bottom. So 36 over, this is going to be 17, right? The 2 negatives and then one numerator, one denominator will cancel each other out. So we have a sub 1, a sub 2, a sub 3. We need 2 more for the first 5 terms. They're going to start to get ugly, right? Now we're in these ugly fractions, so now when we plug them in, it won't be as nice, but we'll do our best, right? This is an example I came up with on the spot. Maybe we'll do it over here. Yeah, we'll do a sub 4 over here. A sub 4 is equal to, and I'm going to skip this step now, right? You can understand this would just be 3 plus 1 here. We'll skip that, right? So I'm just going to write it as this is now 3 a sub 3 over a sub 3 minus 5. So we have 3 times the ugly 36 over 17, all divided by 36 over 17 minus 5. So now we just have a bunch of ugly algebra, right? Okay, so equals, let's do some ugly algebra. 3 times 36, 108. So we have 108 over 17, right? This is in the numerator, divided by our denominator. Well, let's think about this. So maybe we need to do some side work. What do we need? We need a common denominator here of 17, right? So we have to multiply 5 by 17 in the numerator and the denominator. So just so we can see, I'll write it over here. This is going to be 85 over 17. Take a second, pause the video if you don't believe me. And now we need to do 36 minus 85. Right, well, 35 minus 85 would be negative 50, but we need to subtract 1 more, right? So we're at negative 49 over 17. Okay, well the good news is this 17 are going to cancel each other out, and we'll be left with 108, we'll say negative 108 over 49. Maybe not the best example to pick because a sub 5 is about to be strange to solve. So feel free to do a sub 5 on yourself. I don't want to take up the whole video. This problem is not in your homework. I just took your homework problem and tried to make it a little bit more difficult. So a sub 5 would be approached in the same way. I'll set up this first part. Feel free to calculate it on your own. I don't want to take more video time just for pure algebra, but this would be 3a sub 4, which is the ugly number over here, divided by a sub 4 minus 5. All right, so feel free to calculate that on your own. Right, so no difference, right? In this case, it's the same exact problem that we were doing, list the first 5 of the sequence, except it's just defined a little bit differently. The first one was defined with the general term. This one is defined recursively, but no difference in how we go solving them, just a lot of algebra, right? Okay, so we will add some calculus in the next example. I will see you there. So I might have lied. One more question before we get to calculus part. So before we were giving you the general term, right? So I was giving you, let's say, a sub n is equal to some function, and then you were writing out the terms, right? So now what we're going to do is we're going to go the other way. Meaning if I give you some terms, so let's say a sub n is equal to the set, so I'm going to give you the terms now, negative 2 over 9, 3 over 16, negative 4 over 25, and I think we can give you one more here. We'll do 5 over 36, comma, dot, dot, dot. Right, so if I give you some terms, now I want you to find me the function a sub n, right? So find the general term a sub n. I don't want to label this. We'll just call this a for right now. This isn't supposed to be an n here. It'll just look a little blurry. That's fine. Right, so this is just our ordered list here. And I want us to find the general term. This is what I'm supposed to write down here, a sub n. We want to find the actual function that is mapping, right, or making this all work out. So in other words, what we need to write on the side is, right, when I plug in 1, right, say I plug in 1 to my function, I get negative 2/9. Right, that's what's happening here. If I plug in 2, I get 3/16, and so forth, right? We can write all these out. If I plug in 3, I get negative 4 over 25. If I plug in 4, I'm going to get 5 over 36. Okay. So we want to start to break this down, right? And this is kind of just all about pattern recognition, right? So what I'm first going to look for is, what do I notice is curious, right? From 1 to 2 to 3 to 4, right? Well, I'm switching signs, right? I went from negative to positive to negative to positive, right? So I know that if I'm switching signs, that's why I mentioned in a previous example, the alternating piece. I'm going to go ahead and we're going to write out the alternating piece. So I have the alternating negative 1 to the n. And we can see if that's true immediately, right? If I plug in 1, I get a negative number. If I plug in 2, I get a positive number. If I plug in 3, negative, positive. And if I plug in 4, positive. So we're good. The alternating piece has now taken care of the signs. Right, those are done. Okay, so now let's just look at the numerator. What is the relationship between 1 and 2? Well, 2 is 1 more than 1. Same thing here. What is the relationship between 2 and 3? Well, 3 is just 1 more than 2. 4 and 3, 1 more than 3, etc. So in our numerator, right, if I'm plugging in the value of 3 and I'm getting a 4, that means it must be the n value, right, this n, plus 1. All right, so we took care of the signs, the alternating signs. Then we looked at the numerator and we were going from 1 to 2, right? 2 to 3, 3 to 4, 4 to 5. Well, the only way that happens is if we just add 1 to our next number, right? So now that is our numerator. So took care of the alternating piece. We've taken care of the actual coefficient. And now what do we notice here in our denominator, right? Well, what do we notice first before we even get to anything? 9, 16, 25, 36, right? These are all perfect squares. 3 squared, 4 squared, 5 squared, 6 squared. Okay, now how am I going from 1 to 3? I'm adding 2. How am I going from 2 to 4? I'm adding 2. 3 to 5, adding 2. 4 to 6, adding 2. Right, so all of this is just pattern recognition essentially. We had to first recognize that these were perfect squares, or else it might have been hard to be like, well, we're adding 8, we're adding 14, we're adding 22. We wouldn't have found a pattern there. But now that we know they're perfect squares, we know in our denominator, we're going to take our value that we're plugging in, we're going to add 2, right? 1 to 3, 2 to 4, 3 to 5, 4 to 6, and then we need to square it. And we can always go double check. Right, you can always double check. If you go ahead and you write your general term here, this was a mistake up here. If you write your general term, now it should make sense. If I plug in 1, negative 1 to the first power, let's just double check. I get negative 1 to the first power. 1 plus 1 is going to be 2. Right? Oh, did I push? Oh, yeah. 1 plus 2 is going to be 3 squared. There we go. Negative 2/9. And you can check the rest of them if you want, but I don't think there's any reason to go further. So this one I believe is straight out of your homework. I picked it because I thought it was a good example of it's combining a lot of different things, right? It's combining the alternating piece, right? We also need to realize there's a pattern going on with the perfect squares in the numerator, as well as the relationship between our natural number that we're plugging in and our numerator. I think I said numerator here, denominator. So now we will add calculus. So next example, adding calculus. Only one more part to add. I will see you in the next example. Finally, adding the one calculus part to this video. Let's go ahead and begin. Right, so the idea is, let's say I have a sequence. So I'm going to write it out in terms of the general term. A sub n is going to be equal to 2 raised to the n all over 3 to the n plus 1. All right, so I'm giving you some sequence. And I want to know what is the very last, will this sequence converge to a value? Right? What is possibly the last value, or what will this converge to as we're going towards infinity, essentially? Right, so it's going to ask you, will this sequence converge or diverge? Right, essentially we're looking what's happening at the very, very end of this sequence. Are we going to get to a certain value where we just stick on that value, which means we converge? Or will we just keep going on forever? Right, so the way that we do that is we introduce a topic back from the very beginning of 262 with limits. Right, so I'll box this so we have an example. We'll use this later on. And so the idea is, if I can take the limit as a sub n, or as n goes to infinity, of a sub n, and it equals a specific value, right? We'll call it the limit. Then we say that this converges. Right, so if we actually get a value that comes out of this, then we converge. However, if we get the limit as n goes to infinity of a sub n, and it equals, we'll just say plus or minus infinity, right? This does not converge to a specific value, so we say this diverges. These are our two different options here. We take the limit as n goes to infinity, If we get a specific value coming out, we converge, and we're just going to specify what we converge to, I believe, in our problem, or, right, we will diverge. So using the example that we have here, right, let's see if this converges or if this diverges. So again, I'm just going to follow the definition that I've written here. So limit as n goes to infinity of a sub n, right, well, this is the same as the limit as n goes to infinity. And what is my a sub n? Well, it's this 2 raised to the n over 3 raised to the n plus 1. Okay, well, what's throwing us off here? What's throwing us off? The fact that this is raised to the n and this is 3 to the n plus 1, right? That throws us off a little bit. What if they were both n on the top and n on the bottom? Well, we would have something then, right? We could simplify this. So I'm going to write on the side, I know that 3 to the n plus 1 is equal to 3 to the n times 3 to the first, right? These two are equivalent. So when I go to make this simplification now, I'm going to say, well, this is going to be equal to the limit as n goes to infinity. And now I'm going to write this as 2 to the n all over 3 to the n times 3. You could put to the first if you want, but not necessary. And now that I have a constant, this is coming all the way back from 262, beginning of calculus 1, right, even before we did derivatives. If I have a constant here, I can pull this out to the front. So I can write this as 1/3 limit of, let's write n to the infinity, or n goes to infinity, of 2 to the n over 3 to the n. And last algebraic step, one-third limit as n goes to infinity of 2/3 to the n, right? So now, if you think about this, what would happen as I keep multiplying? What's happening here? 2/3 to the n raised to the infinity. What does that go to? What does that go to? Take a second, think about 2/3. If we multiplied it by itself, we'd go to 4/9, 6/27, or nope, 8/27, 16/81, right? We keep getting smaller and smaller, and we're actually going to 0. So this ends up going 1/3. This here will evaluate to be 0. And the good news, even though we're like, well, 0 is a very uninteresting number, well, it still actually converges to a limit, right? That is a value. It doesn't go to plus or minus infinity, so it is converging to this value of 0, right? That is our limit in this case. So this is the answer we're looking for, and we would say that it does indeed converge. Right? Again, if we get plus or minus infinity, then we would diverge. So that is the one bit of calculus we will add in this video. In videos to come, right, we will be doing more calculus. This one was more of an intro to getting used to sequences. Hopefully those first few examples helped. If you have questions, as usual, ask away. Thanks, guys.